Hello, Math 1680 students. I got a request from a student, actually a multiple number of students, about this problem, and it's about multiplication rule. It's about an earn model, and if I remember correctly, this is the same problem as the homework problem. Let me see. Let me go and check. Let's see, is that the same problem? 4 red, 3 blue, 2 green, and 1 black. And here we have 4 red, 3 blue, 2 green, and 1 brown. Okay, it's the same problem. And we have throwing the ball with replacement versus without replacement. Problem number 1 is about without replacement. That is, select a ball and then throw it away so that I have only 9 balls to choose from. And then select another ball and then discard it so that now I only have 8 balls to choose from, and continue. Problem 2 is with replacement. So select a ball and then record a color, put it back in and reshuffle it. And then when I select again, it's exactly the same as the first draw. 10 balls to choose from with same color distribution. And we have to repeat the same problems here. What are the problems here? 2 balls are selected without replacement, and then first is red and second is blue. Okay, all right. I could do this problem, but then again, of course, what's the point? So let me change the problem accordingly. Let me see. Contains, okay, 6 red balls. I'm changing, so I'd better change the name of this file as well. Okay, all right. Okay, all right. And then changes to 6 red balls, and then 5 blue balls, and then 2 green balls. Okay, I'll leave it at 2. And then let me see, how many do I have? 11, 13. Okay, make it 2 brown balls so that the total number of balls here add up to 15. Is it right? 11 and then 13, 15. Okay, the total will be 15. And then let's see, if 2 balls are selected without replacement, what's the probability? First ball is red and the second ball is blue. Okay, all right. Let's change it. If 3 balls are selected without replacement, what's the probability? The first ball is red, the second ball is blue, and the third ball is blue again. Okay, all right, that's as good as any. So basically I'm looking for a sequence of events, red, blue, and blue. So that's basically what I want. Probability of red in my first draw, and blue in my second draw, and then blue again in my third draw. This is what I want. Okay, similar to homework problem, a little bit harder. Okay, let's begin. How do I do this? Well, what is the probability of selecting a red ball in your first draw? There are total 15 balls and there are 6 red balls out there. So use your common sense. And can you see that the probability is 6/15 in your first draw? Okay, that's easy. Next, we have to use the multiplication rule. So we have to multiply the next probability because this is not red or blue about the same draw. First is red and I'm going to blue, and the third is blue, so I'm using and. That's multiplication basically. Okay, let's go to blue. Second draw is blue. Now what's the probability? There are 5 blue balls to choose from, and how many balls are there to choose from total? Is it 15 again? The answer is no, it's 14, only 14, not 15. Why? This is without replacement. We selected first ball, that's red, okay, and that did not go back into an urn. So there are only 14 balls to choose from. 5 of them are blue, so 5, 14 is the next probability to multiply. Now the third draw, how many balls are there total? We started with 15, and then one was selected out, 14. Now another one was selected out. Now I only have only 13. Out of those 13, how many blue balls? 4 of them are blue, because I started off with 5, but second is blue, selected out. So I only have 4 blue balls to choose from. So what's this probability? Punch your calculator, you're going to get something. I'll stop here. What if I do more? What if I do this? 4 balls are selected, and red, blue, third ball is blue, and the is red. The fourth ball is red. In that case, it's basically this. I forgot to highlight this part. Okay, that should be red. And then what do I have to multiply here? Used to be 6 red balls. 1 was selected in my first draw, so there are only 5 red balls to choose from. And then the total balls are now used to 12, and that's going to be my probability. What if I change it like this? The fourth ball is green. In that case, this should be green, and then the probability is going to be different here. How many green balls are there to choose from? 2. And the total number of balls, 14, 15, 13, and then 12. So that's going to be the probability. So does everything make sense? We use multiplication, multiplication, multiplication. Each time I do multiplication. And then please note that the total number of balls are dropping because the next event is based upon appropriate condition that the previous event took place. So the second draw is under the condition the first draw was red. So their total number of balls reduced to 14, and then there are 5 red balls now to choose from. Oh, okay, that's not red, this is blue balls, so number of blue balls did not change. If you go to the third, then okay, alright, the number of blue balls changed to 4 blue balls now, because under these two conditions, you see, these two conditions, first was red and then the next was blue. Under that condition, I have only 4 blue balls to choose from, and then the total balls reduced to 13. So all these probabilities here are conditional. Okay, all right. Let's go over to problem 2. And let me copy and paste this. Excuse me. And this time with replacement. So what's the change here? What's the difference between without replacement versus with replacement? Get the color and then put the ball back in and then reshuffle it. So the total number of balls will stay at 15 all the time, and then the color distribution will remain the same. So the second draw is totally unrelated or independent from the first draw, and the third draw is completely independent from first 2 draws and so on. So It's basically exactly the same as the first draw being repeated. So, first draw 6 out of 15. Next draw, their total. Excuse me, I have yet to change these numbers. And then I've yet to change these. Okay, all right. Okay, let me come back. Excuse me. I forgot to change these accordingly. All right, where was I? Yes. With replacement, there are total 6 red balls to choose out of total 15, so 6/15th. And there are 5 blue balls to choose out of total, again, 15 because I put the ball back in. And then how about the third draw? Blue balls, there were 5. I selected one out, but I put it back in. So the number of blue balls did not reduce. So stay 5/15th. And then green balls, 2/15th. And that's going to be the probability. See the difference here? Without replacement, we have those steady decrease. With replacement, no change. So if you do this kind of thing with replacement, excuse me, then even with 15 balls, I can draw this 25 times. Without replacement, the maximum I can draw is 15 because I'm going to run out of balls. So if you have some long sequence, so green, blue, green, green, brown, that kind of thing is impossible because I cannot select 3 green balls out of total only 2 green balls to choose from. Here, that's okay. The probability, of course, is going to be small because I keep multiplying those small numbers, but anything is possible here. I can do this 100 times, 1,000 times. And for example, how is the second model related in practice? Well, consider this as we're having an election and candidate 1, candidate 2, candidate 3, candidate 4. Excuse me, the total is 15 here, so that doesn't bode very well. So let me come back to the previous problem there. So red previously was 4, blue was 3, green 2, brown 1, okay. So they add up to 10. Okay, that's easier to calculate. So 40% of the people support candidate number 1, 30% support candidate number 2, 20% support candidate number 3, and then 10% candidate number 4 or undecided, whatever. And then we are doing some prediction about the election, and that kind of thing corresponds to the second model. You see, the percentages will not change by simply selecting 2 or 3 people out of some hundreds of million people, you see. So these problems are, as a matter of fact, realistic. Okay, so much for the first problem, and let's talk about the second problems in a separate video.